our analysis. All right, so let's go back to these delta y's, and I'm going to call this problem A, problem B, and problem C, okay? So in problem A, the question is, what is the ball's delta y, meaning its change in vertical position from its initial to its final moment? So we're specifically talking about this. What is the ball's delta y from here to here, right? In other words, how high does it rise? So that's here, okay? Delta y, we're going to use equation 1 from our big 3 kinematic equations. Okay, and equation 1 tells us that the change in vertical position is v initial times t plus 1/2 a t squared. Okay, the initial vertical velocity is 29.4 meters per second. And from the initial to final moment, that means while it's rising, it doesn't reach the peak for 3 seconds, right? So I'm going from my t initial to t final, right? Here. Okay, continuing on. I'm going to add half of the acceleration. It's accelerating at negative 9.8 meters per second squared. And then my time, again, is 3 seconds, right? Because it rises for 3 seconds. If I plug that into my calculator, I get 44.1 meters. So that is literally how high the ball goes from where it was released. So this is 44.1 meters on the diagram, okay? Let's look at problem B. So now I don't want to know how high it goes. I want to know how far it falls. So in this next problem here, when the ball is falling, what's the delta y? Well, now when the ball is falling, the delta y is from here all the way down to here. Okay, how far does it fall from its peak? So this is problem B, okay? Now I'm going to look at this time interval from 3 to 7 seconds. Okay, so here we go. Delta y now, while it's falling, I can use the same equation, but the v initial is different. Now v initial is 0, right? Because it's starting from the peak. And then how long does it fall? Well, from 3 to 7 seconds, that's a change of 4 seconds. It's falling for 4 seconds. Half the acceleration. And again, a 4-second fall, squaring that. So this obviously goes away, and I'm going to get negative 78.4 meters. Negative because it's falling, right? It's moving down. Its displacement is in the negative direction. Okay, question C now. Now we're going to move to here. What is the change in vertical position on the entire trip? Now we're looking at here. And this one's a little bit trickier. So, and I forgot to write this part in. This is negative 78.4 meters. Okay, so now on the entire trip, we're now going to go from here, right where the ball leaves the boy's hand, to here just before it hits the ground. So now what is that delta y? Okay. Well, the ball's going to rise to the peak and then fall back down to the ground. So we're going to use the entire trip from 0 to 7 seconds when we plug in our time interval. All right, so here we go. And another way that problems often ask this question is, how high was the cliff, right? Or how high was the boy's hand when he released the ball? So here we go, question C. Now, if I just plug in the equation, I will get a reasonable answer. And so the initial velocity is 29.4, because that's how fast the boy throws the ball. The time now is, right, it's from 0 to 7. So the change in time is 7 seconds. Still accelerating at negative 9.8 meters per second squared for 7 seconds. Okay, so if I plug in this, I actually get a negative number indicating, right, that the ball is moving down from its starting place. So this is a 34.3 meter high cliff. And I'm getting a negative number because the ball is moving down, right? Is there a more conceptual way that I could have gotten this answer? For sure, because I already knew how high the ball rose, right? I already knew this delta y, and I already knew this delta y. So couldn't I have just subtracted them? For sure. In other words, delta y total is equal to the change in position while it's rising, right? Plus the change in position while it's falling. I already got the change in position while it was rising. That was the 44.1. And I already got the change in position while it was falling. That was the negative 78.4. And so, of course, when I add those up, I get the same thing, negative 34.3 meters. So no matter how you do it, right, you're going to get the same response. So again, this is how to understand the importance of choosing your time interval when making an analysis on motions or on problems involving acceleration, involving initial and final moments, and how it can be very strategic to choose maybe just the rising motion or just the falling motion or the whole trip.